Yeah, okay, sir. Murugan sir, can you start, sir? Ma'am, can we start, ma'am?
Yes, sir. Shall I present the screen, sir?
Yes, ma'am. Yes, ma'am. I'll just give an introduction and then you can start, ma'am. You can share the screen, ma'am. Present now. Good afternoon, dear participants. Here we are for session 2 of day 4 of the AICTE short-term training program on FEA. We have a guest, Dr. K.R. Padmavati from Panimal Engineering College, Chennai. She's an associate professor of Department of Mechanical Engineering. Today's session is going to be on role of finite element method in nanotechnology research. To introduce the guest, Dr. K.R. Padmavati completed her PhD in the Department of Mechanical Engineering, Satyabama Institute of Science and Technology, deemed to be university. She has completed her bachelor degree in mechanical engineering in 1995 from PSNA College of Engineering and Technology, Dindukal, Madurai Kamaraj University, Tamil Nadu, India. She obtained a master's in engineering in computer integrated manufacturing from College of Engineering, Guindy, Anna University, Chennai, India in 2007 with distinction and gold medal. She has around 20 years of experience in teaching in various institutions. At present, she is working as the Associate Professor in the Department of Mechanical Engineering, Panimal Engineering College, Chennai. She has published more than 20 journal papers in various reputed international journals. Her research interests include fabrication, mechanical characterization, and tribological studies of metal matrix composites, modern manufacturing systems, and finite element analysis of composite materials. We welcome you, ma'am.
Thank you, sir.
The session is yours, ma'am. Thank you.
Yes. Good afternoon, everyone. I hope my screen is visible to you.
Yes, ma'am. Can you put it on full
Yes,
screen?
yes, ma'am.
Yes, ma'am. Thank you, ma'am.
Yeah, I'm K.R. Padmavati. I'm going to present about role of finite element method in nanotechnology research for a AICTE sponsored STTP on fundamentals of finite element analysis and its applications in engineering, organized by Panimal Institute of Technology. So we all know about what is finite element method is, and what is nanotechnology as well. Okay, and how today everywhere people are speaking about nanotechnology, nano, everything. So how finite element analysis is finite element analysis or finite element method is helping in the nanotechnology research field. So few of the researchers, I'll just explain how they have implemented finite element method in the nanotechnology research. And we all know what is finite element method is. It is a numerical method of solving problems of partial differential equations. You would have come across several sessions in this STTP. And it is a method of dividing up a very complicated problem into smaller elements that can be solved in relation to each other. That is what is discretizing it into smaller elements and that can be solved in relation to each other. And also we know all the structures and machine components are usually three-dimensional members, And the properties are analyzed with the help of one-dimensional, two-dimensional, or three-dimensional techniques based on their dimensional ratios. If we say is one-dimensional problem, it is with which one dimension is very large. It may be a length, or in one direction, that is in x-axis, you have a larger dimension. If it is a two-dimensional problem, one dimension is very small, negligible dimension, thickness we can omit it. And if it is three-dimensional problem, all the three dimensionals are large. And we have special cases like axisymmetric problems. And if it is axisymmetric solid or solids of revolution, we can use the axisymmetric elements for solving the problems. And also, most of the engineering problems are like solved with the help of a triangular elements, that is CST elements or quadrilateral elements. And even if it is a complicated problem, it will be solved with the help of it would have solved with the help of higher order elements. With the help of higher order elements, it has been solved. And about nanotechnology, you all know it is a study of manipulating matter on an atomic scale. Okay, that is nano is to the size of 10 power minus 9 meters, we all know. And it refers to the construction and engineering of the functional systems at a very micro level, that is at a very micro level or at an atomic level, we can say. And this is what is about micro, macro, and what is nano is. Macro will be able to measure or vision. We can have a vision. That is, for example, if you take a fruit apple, it varies from 6 to 8 centimeters. It is actually 80 million nanometer. An ant will be able to see the height of a person. In the same way, if it is in micro size, the human hair, it is to the size of 75,000 nanometer size. Okay, that is whatever we can able to view is actually, the eye can see is actually 10,000 nanometers only. Okay, so if it is below that, with the help of microscopes, we'll be viewing it. Okay, and if it is, these are all actually in nanometer size, that is buckyball, it is actually a carbon atom, one of the varieties of carbons, to the size of 1 nanometer, DNA to the size of 2 nanometers, and we have carbon nanotubes to the size of 1.3 nanometers. We have different single-walled, multi-walled carbon nanotubes. Nowadays, we have graphenes. So everything will be in nanometer size only. Okay, and all these nanometer particles or tubes are used in the nano field or in nano research. And several applications of nanotechnology, we all know, like in several fields, almost in all the fields of engineering, the nanotechnology plays an important role, starting with the energy field, medicine, producing nano devices, nano components. Nowadays, each and every day, there is a new model mobile is introduced. So there are several components, minute, smaller components are there, and which can be applicable in space research, optical engineering, defense and security, biomedical engineering. In biomedical engineering, it is nano-sized some implant surgeries. With the help of this nanotechnology, they have produced smaller components and which can be inserted into the blood cells for curing certain diseases like cancer and all. And like even in the cosmetics field, like I've studied research in which they have used nano titanium oxide particles in the cosmetics, like for giving sunscreen protection and all. And nano fabrics nowadays, the nano fabrics, the cloths, the shirts. If tea, coffee, or a water is spilled out on a shirt or a cloth, it won't absorb. The cloth won't absorb the water or a fluid. Okay, it will be rounded off easily. We can clean that fluid from the cloths. So those are the nano fabrics. In several fields, the nanotechnology plays a major important role. And in mechanically, we have modern developments like atomic force microscope, with which we have a nano tip, atomic level tip. We have to identify the surface characteristics or characterizing the materials. And even we have scanning tunneling microscopes, which have the scanning probes in an atomic level. That actually launched the nanotechnology. And this is just to have a brief about what is, we all know how much is millimeter, micrometer, nanometer. Nanometer is actually 10 power minus 9. like pico, femto, atto. Atto is 10 power minus 18. Okay, why I'm showing this is actually now we are facing a problem due to a coronavirus. So that is why this session is also due in online. We are conducting this STTP. That is, we everywhere we are seeing this stay home, stay safe slogan. So why? Because it's due to the coronavirus, which actually affecting us. It creates a pandemic, and it is destroying several lives in the world. Okay, and you see how much smaller it is. It weighs actually 0.85 attogram. As I've told you, attogram is actually 10 power minus 18. So this much of 0.85 into 10 power minus 18 gram is actually the weight of one coronavirus. For example, if you take a particle of 0.85 gram and we divide it into 10 lakh parts, and with that 10 lakh parts, you can take one piece and further you can divide it into 10 million parts. And with this 10 million parts, if you take one particular part, that is actually the coronaviruses. Okay, so the weight is actually 0.85 attogram of it. So this is actually affecting the human beings. If a person is having 70 billion coronavirus only, he'll be tested positive. He is positive with the coronavirus. So all the 70 billion coronavirus in it weighs only 5 into 10 power minus 7 grams only. All the 70 billion. So this is actually causing us to stay home, stay safe, and is creating pandemic now. Okay, and several mechanical instruments for measuring the viruses to look at the viruses are useful. That is suspended microchannel resonator. Even now, suspended nanochannel resonators are the instruments used for measuring this. Measuring and viewing, analyzing the coronaviruses. Okay, so why I'm telling all these things is when I'm giving a topic to Dr. Murugan sir about role of finite element method in nanotechnology research, I found an interesting paper. This is what is a potential treatment for COVID-19 based on modal characteristics and dynamic responses analysis of 2019 NCOV, that is novel coronavirus. So this research paper I have seen, it looks very interesting. So they are using the concept of modal analysis. So whatever we do in ANSYS, modal analysis, that is getting dynamic responses analysis. So this is what modal and harmonic analysis we study in ANSYS or in FE. So that concept they have used, and they have tried to actually, these are the spikes. It is like a spear ball in which it has several spikes. Actually, they are trying to spoil or damage this spikes. Actually, which has the proteins, which is actually helpful in spreading the virus into cells of the human body. Okay, so if they destroy this spikes, it won't spread further into the human body. So they made an attempt. That is what is here, a potential treatment for COVID-19 based on modal characteristics and dynamic response analysis of 2019 novel coronavirus. So that is why I'm explaining about what is coronavirus and how much smaller it is, how it is spreading into human beings and all. And the basis for this paper is actually whatever we do as a modal analysis in finite element analysis, that is FEM or FE. And we all know about, I'll just brief about modal analysis. Actually, the goal of modal analysis in structural mechanics is to determine the natural mode of shapes and frequencies of an object or a structure during its free vibration. What happens to the structure? And it is the study of dynamic properties of the systems in the frequency domain. And like examples, we can measure the vibration of a car's body when it is attached to a shaker, or the noise pattern in a room, okay, when it is excited by a loudspeaker. So in this way, we do modal analysis and what happens to the structure. And this is a simple procedure. So if you want to do a modal analysis of a cantilever beam, and why I'm again telling about the cantilever beam is, here this is a spear. They are considering this spear as fixed, and all these spikes they are considering as cantilever beams. This is a cantilever beam, this is a cantilever beam they are considering. That is, this end is fixed, that is, this sphere is fixed, and this one they are this spike protein they are considering as a cantilever beam for doing the analysis for this, for in this research paper. Okay, so that is why I'm just depicting how to do a modal analysis in FEA. That is, we do, for example, this is a spear where the spike is, the protein spike is attached with the spear ball of a coronavirus. So in this manner, this is a mechanical example, and first we'll do the pre-processing steps. We'll prepare a model of a cantilever beam. We'll specify, we'll do model it. We'll specify the material properties, everything. We do meshing, all those things. And on the second stage, on the solution stage, we'll assign the loads to solve it. That is like analysis type, we'll choose what type of analysis we want to perform, model analysis. And in analysis options, we have to choose by which method you have to extract the mode shapes. So different mode shapes we'll get for this beam, for this cantilever beam. So in what way we have to get? Usually it is by default, it will be the reduced method will be selected. So it will be considering the major degree of freedom, for which it shows us like it shows us the mode shapes. But here, if you take subsurface, what are the points or what are the major degrees of freedoms we want to get? For that, we'll be getting the mode shapes, and how many number of mode shapes you want to extract. All these details we have to give. And actually also by specifying all these things, it will give us another window to show where you have to fix up all those things. You have to specify rigid body mode, you have to specify starting ending frequencies. So all these things you have to fix up, and it will show us the results. Okay, here actually they have specified 5 mode shapes, so 5 different frequencies on which it shows us the results, and 5 different mode shapes of the cantilever beam are displayed here. Okay, this is the basis of doing modal analysis in FEA. So this concept actually they have implemented in their paper. So the paper, whatever I have shown you, a potential treatment, they are considering this as a treatment for COVID-19 based on modal characteristics and dynamic response analysis of 2019 novel coronavirus. That is, their abstract is actually that is we all know it is actually destroying the world. That is, it is ravaging the world, taking lots of life, and it is emergent to find a solution to deal with the novel phenomena, pneumonia. And nowadays we are getting vaccines, and it has been introduced to the people. Several people are taking it now, and they have attempted it last year. And it provides a potential treatment for COVID-19 utilizing a resonance to destroy the infection ability of this coronavirus. Okay, those spikes are destroyed. If it is destroyed, it won't spread further in the human blood cells. That is their aim. It is actually, the geometry is actually scaled up to 10,000 times, since it is in autometer size, so that is in nano size. So you cannot draw it, you cannot model it quickly. So it is scaled up to 10,000 times. And also the additional mass is used to represent the effect of fluid around the spike protein, that is the blood around the spike protein. And here they are using the finite element analysis concept to study the modal characteristics of the tuned novel coronavirus and also mistuned novel coronavirus model in the blood respectively. Okay, that is based on the finite element analysis and the lumped parameter mechanical model of this coronavirus is established. Okay, actually they are what they are actually trying to do is the dynamic response of the mistuned novel coronavirus are investigated through harmonic response and dynamic analysis. And finally, a potential method utilizing 360-degree sweep excitation to cure COVID-19 is put forward. Okay, that is giving resonance to the human body using this 360-degree sweep excitation method. So they are trying to destroy the coronavirus spikes. Okay, actually here, this paper actually tries to provide a potential method based on the vibration to damage the infectivity of the coronavirus and cure the coronavirus, cure the COVID-19. Actually, it consists of a virus spear that is actually fixed, and it has several spike proteins around it. Okay, and if it infects the humans, they enter the cells of the human body, and by binding their spike proteins to the receptors on the cell membrane. So these spike proteins which hits the cell membrane and then which copy the viruses into the cell. So several copies were made in the human blood cells. Okay, so this is actually theoretically it is feasible to disable this coronavirus by destroying the spike protein structures. As I've already told you, they are trying to destroy the spike protein structures through the resonance, and that is easy for the immune system to eliminate these viruses and we can recover. Okay, so this paper actually they have explained, they have combined finite element analysis and also theoretical methods to study the modal characteristics and the dynamic responses of the virus. And this is what is actually, in this way, they have modeled the coronavirus using actually SolidWorks. Using a SolidWorks CAD software, they have modeled this coronavirus, their spear, and with several spikes they have. That is actually the geometry size of this virus is about 200 nanometers. And for their convenience, they have made it actually, they have scaled up to 10,000 times, and they have considered it as a 2 mm size. The size of the virus they have considered as 2 mm. Okay, and all the other parameters, that is this length of the spike, everything are magnified by 10,000 times. Okay, once after getting the results, it can be scaled down again by 10,000 times. Okay, so this is what is actually, and as I've already told you, each and every spike structure they have considered as a cantilever structure. Okay, this spear ball, this is fixed, and from where there is a cantilever. In that way, they have considered, and it is reasonable to apply the traditional mechanical methods to conduct the analysis. Okay, so by considering in that way, we can do finite element analysis. That is what they're exposing, and it is actually, as I've told you, it is built using SolidWorks, and from there it is exported to the ANSYS workbench to carry out the modal analysis. And in this way they have got the results. Actually, this is actually model shape of one spike protein. What happens if a particular resonance is applied to the spikes? So different mode shapes they are obtaining. Actually, they're considering the mass, the pre-processing stage. They're considering the mass to represent the effect of fluid around the structure. And actually, the additional mass of the blood per unit length around the spike protein, they have calculated it using this formulation. Okay, it is actually considering the density of the blood, equivalent radius of the environment, and radius of the spike protein, smaller or. Okay, since R is infinite, the radius of R is actually the equivalent radius of the environment. It is infinite. It spreads throughout the body. We will not be able to get it exactly. So they have simplified the formulation for getting the mass of the blood per unit length as rho b into pi r square. So in this way, they have taken several input parameters. So we do in pre-processing stage of ANSYS. So in that way, so it is because of relatively heavy mass of the spear body to the spike proteins compared to the spike proteins, its modes or rigid body motion they have considered, where the spear of the model is fixed in modal analysis. And as I've already told you, that is, which has each and every spike protein. It has several spike proteins, so each and every spike protein has a different frequency, and it would be possible to utilize. That is, for destroying it, they are using the ultrasonic vibration exciter to 360 degrees sweep. So around the whole virus in 360 degrees, they are applying the ultrasonic vibration using an ultrasonic vibration exciter. Okay, so to a certain frequency they are applying, and given a proper excitation amplitude, it would destroy the spike protein structures and disable the infectivity of the virus. And some strength, the bending strength of the spike protein is actually unknown, and they have compared it with the steel which is having a bending strength of 300 megapascal. So if a stress in the spike protein is bigger than this 300 megapascal, it will crack at the base. So the base of the spike protein can be damaged, and it loses its ability to invade the human cells. Okay, so the required destruction excitation amplitude is analyzed by the FEA. So what is the excitation amplitude has to be applied is analyzed by FEA, and which is calculated as this much deformation, and the equivalent acceleration they have got is 4.164 meter per second square. So based on several studies with several researchers, the resonant frequencies of the standing human bodies was found to be from 9 to 16 hertz to the maximum 20 hertz or below 20 hertz will be able to withstand the resonant frequency of a standing human body. So it would be it would not cause much harm to the patients if they are if they have applied with ultrasonic vibration, with the help of ultrasonic vibration exciter. That is what is they are trying to say here, and it is efficient and safe to utilize an ultrasonic vibration exciter to conduct 360-degree rotation sweep excitation to the human body. And finally, they have concluded as to help curing this virus, they have utilized this 360-degree sweep excitation to destroy the spike protein structures, and the vibration range they have found, and it is efficient and safe to disable the novel coronavirus. So this is what they have tried to see, and here the FEM, the analysis, played a major role. Finite element method plays a major role in identifying the frequencies. That is, they did harmonic and the modal analysis. And while searching for research papers, in several research papers, if it is nanotechnology or nano research, several papers are there with the nano indentation. Nano indentation is, if it is indentation, it comes to our mind that finding the hardness of a material we used to find. That is what is. And if we have several hardness testing methods like Rockwell, Brinell, Vickers, Knoop hardness, several are there. Okay, and actually here, by doing this nano indentation, two mechanical properties like elastic modulus and hardness and several other parameters from this can be identified by doing just nano indentation method. And several papers are based on this phenomenon and nano indentation. And the elastic modulus, it is actually an intrinsic property of the material. At fundamental level, we all know it is a measure of the bonding strength between the atoms. Elastic modulus, E, is actually, if the modulus is greater, it is stiffer the material and smaller the strain. And nano hardness testing actually refers to hardness tests wherein the depth of the indentation is usually less than about 50 nanometer. We all know how much is 1 nanometer is 1 into 10 power minus 9 meters. So the depth is actually less than 50 nanometer, or equivalently the indentation diameter or length is lower than about 150 nanometer. So this is what is happening in nano indentation, that is in nano hardness testing. And it is actually called as the depth sensing indentation, we can say, also the instrumented indentation, we can say. So it is a method gained popularity with the development of machines that can record small load and displacement. So if we do tensile testing, we'll be measuring this load displacement. We get load displacement curves, we get stress strain curves. So in that way, we have now machineries that can record even a very smaller load and displacement curves. with very high accuracy and precision we can do. And also analytical methods by which these load and displacement data can be used to determine the modulus, the hardness, and several other mechanical properties from these by just doing a single nano indentation testing. And this is what is actually the comparison between micro and nano indentation. This is actually an indenter, pyramid indenter, which is used in Vickers micro hardness testing machine. Okay, it is actually a micro indentation, we say. So it is where the load applied to an indenter in contact with the specimen, and the load is then removed and the area of the residual impression is measured. Okay, how much impression is formed over the workpiece is measured. That is the diagonals d1 plus d2 divided by 2, they are taking as d, and how much load they are applying, with which they can measure the Vickers hardness. This is what is micro indentation. If it is nano indentation, a prescribed load is applied to an indenter in contact with the specimen. As the load is applied, the depth of the penetration is measured, and the area of contact at the full load is determined by the depth of the impression and the known angle or radius of the indenter. I'll show you how the nano indenter will be. Berkovich indenter is used, and the hardness is found by dividing the load by the area of contact, and the shape of the loading and unloading curve provides the measure of elastic modulus. So this loading and unloading curve will get out of the nano indentation instruments. That is, this is actually a loading curve. So how much load you can apply through the indenter on the workpiece surface, and when you are remove it will be there a dull period of 15 seconds or 10 seconds will keep, and after which we'll unload it. This curve is actually an unloading curve. Okay, and with which if you draw a tangent and take a slope, you'll get the rate of loading to displacement, how much it is. So this is what is about comparing nano and micro indentation. So here it shows clearly actually when a maximum load is applied, how much will be the maximum depth obtained. So that is what is shown here. So we can get the hardness value, nano hardness value, whatever be the load applied to the cross-sectional area. That is area, we can find it out with A into HC, that is what is the depth and what is the surface area at this level. And elastic modulus also we can find out by doing nano indentation test. Okay, so this is what is, that is the here A is the projected area of the indentation at the contact depth of HC. This is what it is at initial stage. So the curve is actually in this manner, zigzag manner. Here for our understanding, it is shown as this is loading curve and this is unloading curve. We can get a slope here, so that is used to find out the X modulus or elastic modulus. Okay, so in when we are speaking about Rockwell hardness and all, we use different scales, B scale, C scales, different scales of measurements we'll use for measuring the hardness. Okay, like Shore hardness, Vickers hardness, Mohs hardness, Knoop hardness, everything. So for all these represent actually the relative hardness of the material with reference to a standard sample. So to remove this ambiguity in different scalings, so nano indentation actually provides physical measurement in terms of absolute hardness only. And as an analysis result out of nano indentation, we can get the reduced modulus first. That is modulus of modulus of the specimen we'll be finding out using this formulation. Several researchers have derived several derivations. This is one among it. We can get the modulus of the specimen, and we can find out the stiffness. We can get the contact area. Actually, this nano indentation with the help of Berkovich indenter, it has been carried out. As we say here, a spherical. We have a pyramidal indenter here for doing Vickers micro hardness. Berkovich indenter is useful for doing the nano indentation. We can measure the hardness, we can measure the elastic modulus, okay, using these formulations. So this is actually a like with the help of an atomic force microscope, this image was taken. That is the indentation in left, image of an indent left by a Berkovich tip So this is also a image of indentation on a workpiece with the help of a Berkovich tip. This is actually the tip of the indenter which is used in nano indentation test. So several we know about different types of indenters which are used in different types of hardness like Vickers, Snoop. We had conical indenters. We have spherical. What type of indenter is useful in Rockwell hardness testing? All those things. So mainly in nano indentation, they are using this Berkovich tip, which is having dimensions 3-sided tip it has. And based on this, how finite element modeling of by doing nano indentation will not be able to get all the details. Several mechanical properties will be able to measure. So nano, if you go for nano size research, how much cost we have to, the cost we have to spend for doing testing is more, and also like several equipments are not not present to do the nano size characterization and all. So this can be simulated with the help of FEM or FEA, so with which you can able to measure the mechanical properties quickly. So that is what is actually here. So this these researchers have actually did finite element modeling of nano indentation technique to characterize thin film coatings. So they have fabricated this thin film coatings, and with which they did finite element modeling using for the nano indentation technique to characterize their thin film coatings. So this was the research work. Actually, many techniques are available to service the performance of the coatings. And nano indentation technique is a versatile, non-destructive testing. A very minute nanometer level only the impression is formed over the surface, so it won't affect the material's property. Okay, and it is imperative to simulate the nano indentation by powerful FEM softwares to extract plenty of mechanical properties like hardness, elastic modulus, endurance loads, and various parameters like optimal thickness, optimal critical load, stress distribution, what is the contact pressure between the substrate, that is the workpiece, over which the layer of coating is applied, okay, and which can be measured with the help of load displacement curve. So with the several calculations I've shown you here, so with which by doing nano indentation we can get several mechanical properties, so which can be simulated with the help of FEM software to find out all these parameters. That is what is actually here. Actually, they have reviewed a detailed procedure of nano indentation experiment, and its finite element analysis have been presented, and the latest development in these area have been provided with them while keeping focus on these thin films they have interpreted here in this journal. So this is actually the instrument for doing nano indentation, and here is actually the indenter tip which is doing impression, that is which is doing testing over the sample. So out of this experiment they've got this loading and unloading curve, as I've already told you, so with which this rate of indentation load to the displacement we can get by a slope drawing during the on the unloading curve. So here the finite element method is considered as a valid candidate to have the stress distribution and displacement plot during loading and unloading process. They've got an experimental nano indentation procedure has the limitation of thermal drift. That is, if they conduct, since it is a nano size instrument, so on a precise room environment in a critical with a critical temperature level, they have to do the testing. And so, due to the thermal drift at high temperature environments, which leads to error in the results if they do nano indentation experimentally. So simulation with the help of FEM or FEA can overcome this difficulty of thermal drifting. And therefore, it has been stated by many authors that finite element method is an appropriate method to determine the mechanical properties of materials. And some researchers have employed finite element methods to investigate the indentation process as told you, nano indentation process by considering appropriate dimensions of the sample materials, as well as what will be the sample material with the appropriate dimension, as well as the nano indenter and the indentation depth. And the nano indentation technique can be simulated easily with the help of a FEE. So this is what is actually they did. Actually, this is actually an axisymmetric model, 3D axisymmetric model, axisymmetric concept, axisymmetric elements. Here the elements used are quadrilateral elements, quadrilateral higher order elements they have used, and they have just modeled it like this. That is how much load they are applying. This is the indenter tip, Berkovich tip, and this is the thin film coating they have applied over the substrate. This is a workpiece material over which they have applied a coating, and this is the indenter. So that is modeled with a 3D 3D axisymmetric model. This is the axisymmetric model they did it. Okay, and they have meshed it. They have applied the load. So the loading will be in very low level, very minimum loading in nano level. They will be applying the load. That is what. That is here the finite element simulation of the nano indentation. Whatever they do experimentally, that is simulated here in FE or FEM. Nano indentation can be used to understand the stress distributions when displacement is large and the specimen deforms plastically. So we do this for our normal experimental work. That is, if we do a normal analysis of a structural problem. So it follows that a list of outputs like stress strain fields, stresses at the substrate coating surface, indented material dynamic interaction, thermal effects. So all these things we can we can extract all these details. Those cannot be experimentally evaluated. So these details we can extract from the software if you do the simulation of nano indentation using finite element method or finite element analysis. So that is what we are insisting. And there is another research here also, the assessment of nano indentation method in mechanical characterization of heterogeneous nano composite materials using experimental and computational approaches. So this is what here again they have used, that is to study and investigate the capacity of the nano indentation method in the mechanical characterization of heterogeneous dental restorative nanocomposite, and using the experimental as well as the computational approaches. Okay, they have selected this as the particle Filtech Z350 XT as their workpiece material, selected as a nanoparticle reinforced polymer with a specific particle size of 50 nanometer to 4 micrometer size they have taken. So within the range of indenter, a contact area of nano indentation experiment. A sufficient number of nano indentation tests were performed in various locations of nano composites to extract the hardness and elastic modulus with the help of a loading and unloading curve, load displacement curve, from which they have got. So these are the hardness values they can get with the maximum load applied to the area of cross section, and how they are finding out the elastic modulus, and how the formulations whatever I have depicted earlier, the same formulations they have followed here also to find out the elastic modulus and the hardness of the material. And this is a model they have developed, that is evaluation of the finite element model and simulation process. Okay, this is actually the experimental procedure. So in finite element simulations, so the same model has been created in the microscale. Development of the physical constructions, regular and irregular models, and defining the mechanical properties, applying loading and boundary conditions as we do in all the three stages, pre-processing, processing stage, and predicting the load displacement curves of the six different models, whatever they have developed. Okay. And if all the finite element results within the range of experimental data, they'll proceed to get the final answer. The evaluation of the appropriateness of nano indentation test for the characterization of nanoparticles, that is of the dentin nanocomposite material they have preferred. This is a model they have developed by FE. So this is what is actually the schematic view of the particles, that is the matrix and the nanocomposite particles they have chosen. It is modeled, and these are actually like after modeling we do meshing. So that is what is here. They have meshed it, the mesh pattern of the indenda. This is a indenda, that is and the nanocomposite specimen is regular particle distribution, and they have also considered irregular particle distribution if it is there. So they have compared these two results. So that is what is shown here, the meshing pattern. And these are several load displacement curves. So I have here I have shown you a single load displacement curve. This is a single load displacement curve if you do 1 nano indentation. So here they have compared for their composites on several places at 0.1, 2, 3, 4 and all. So on several places they have compared. They have this is actually the loading and unloading curve. Here the finite element results indicated the load displacement data varies with respect to the indentation location. Okay, so on different locations they have taken. Here they have identified that the one is higher, that is where they have taken at 0.1 is higher than the corresponding values of the indentation. It's 0.213 on the second and third points. Comparing with these two, this is higher they are depicting actually. So these such variations indicate the dependency of the nano indentation results to the location of the indentation. So these are the impressions. Actually, they have done it with the Abaqus software. Yeah, they have done it. These are the deformation and the stress distribution data they have taken for regular model and for irregular models. So as a conclusion, the simulation results of the nano indentation experiment on the dental nanocomposite verified the experimental observations. So the simulation results actually revealed that the contact area of the specimen with the indenda was an axisymmetric triangle instead of the equilateral triangle. So they have come to a conclusion. Instead of doing a experimental nano indentation, we can, that is what is actually the concept as specified here. We can extract more information if you do simulation. That is what. And here actually another example, another researcher did indentation analysis methods explained with the finite element simulation. So this is the model they have. This is actually the indenda. This is the workpiece model. And here we can see, as we do fine meshing at the point of contact of the indenda and the point of contact, that is where the load is applied. So on those places they have finite meshing. Here also they have used a higher order quadrilateral element they have used. So here these are like the simulated results, the displacements on y direction under loading of, under a particular loading, how it should be. So in this way we can do the analysis, that is doing nano indentation. We can simulate the nano indentation with the help of finite element simulations or finite element methods. And another researcher also they have did finite element analysis of composite materials for aerospace applications, the material which is useful in aerospace applications. So for which they are doing they are they're fabricating a composite material and they are testing it with the finite element analysis, and they can compare. And also another paper, another researcher, he has actually found the hardness and yield strength of a dentin from simulated nano indentation test. So from the simulated, using the finite element method, they have simulated it. That is, they have got the values of hardness and yield strength of a dentin. That is actually their workpiece they are considering as using the Abaqus. And here also you see the test is performed with the spherical indenda and simulated by axisymmetric finite element analysis. Okay, they have got hardness, yield strength, modulus, everything. And another researcher actually discussed about the role of finite element analysis in nanotechnology research. Okay, and several techniques, that is the finite element analysis in the field of nanotechnology is actually continually contributing to the areas ranging from electronics, microcomputing, material science, engineering, biotechnology, medicine, aerospace. In different environments, we can use this concept of nanotechnology. So FEM is helping it actually. The finite element method is widely used for solving problems of traditional fields of engineering and nano research, where experimental analysis is unaffordable. Wherever the experimental analysis is unaffordable, we can in the nano research field we can simulate it with the help of finite element analysis or finite element method. Okay, and he has also reported about over decades this method has become the noted research area for the mathematicians. Also, the popularity of this finite element method is due to the advent of computer finite element softwares. We have several softwares now available as Astra, ANSYS, Abacus, MATLAB, OpenFOAM, etc. So, with the development of nanoscience, the researchers found difficulties in spending funds for the nano-related projects. Since if it goes for nano size, as an example, if for my research I bought nano silicon carbide, nano titanium oxide, multi-wall carbon nanotubes, all those things I've purchased. 5 grams of multi-wall carbon nanotube costs around 10,000. 25 grams of nano silicon carbide costs around 7,500. 25 grams of nano titanium oxide costs around 5,000. So the cost or the fund and doing testing over the nanomaterials, whatever we are fabricating. So the cost involved in the nano research, like which can be actually the researchers are finding difficulties in spending funds for the nano related projects. Actually, the FEA has evolved an adorable methodology and offers solutions to all the complicated systems of research. That is what. And actually, several numerical approximations can be reached by differential equations of PD, whatever we do in FEA, for various mathematical and nanotechnology problems. So whatever be the field problem or whatever be the engineering problem it is, we can define it with PDE, partial differential equations. And FEM explores checking the validity of the analytical studies of this nanotechnology. Nanotechnology problems also been defined with the PDEs, so which can be easily solved with FEA or FEM. That is what. Moreover, the unaffordable experimental setup for doing the nano research could be replaced with FEA software. Even now, for taking SEM, TEM and all, how much we are spending, we all know. For taking a SEM sample, we are spending around 500, 600 rupees. For taking a TEM, we are spending, for a single sample, we are spending 5,000 rupees for taking a measurement. Okay. So in this way, the unaffordable experimental setup for doing the nano research could be replaced with FEA software. So that is what is actually here. And this is again finite element simulation of micro machining of nano-sized silicon carbide particle reinforced composite materials based on a cohesive zone model. Okay, it is actually cohesive zone model is actually which is a term used in fracture mechanics, in which fracture formation is regarded as a gradual phenomenon in which separation of the surface involved in the crack take place across an extended crack tip or a cohesive zone, and is restricted by the cohesive tractions. So it is a concept used in fracture mechanics. And also the concept of molecular dynamics, it is a computer simulation method for analyzing the physical movements of the atoms and molecules. So using this concept, these researchers have done finite element simulation of micro machining of the nano-sized silicon carbide particle reinforced composite materials. And this is what, in this way, they have modeled the tooling and the workpiece, and they have arrested these two sides, bottom and the right side of the workpiece, and they have, that is actually the used plane strain coupled thermomechanical finite element analysis. Finite elements they have used to define or they have used to discretize the workpiece, and they have used plane strain coupled thermomechanical finite elements for defining the tooling. Okay, so as we do the analysis, they have simulated this micro machining also over the workpiece with the help of a tool. And several researchers are there. They have used they have studied about the perspective on nanotips, like as I've told you, in scanning tunneling microscopes or in atomic force microscopes and all. You have a atomic size, you have a very very smaller tip, you have in micron size tips you have, which actually those tips of the tips which actually scrolls over the surface, or with the help of a tapping mode, they will just move over the surface, and which will identify or which will characterize the materials. Okay, so studying about the nanotips, several researchers have studied about the nanotips, which are found to behave as a source of self-collimated electron or ion beam, which are used in microscopes. So this is about that particular case. Here also, the tips may get damaged if it moves over the surface of the material. Okay, that is, for example, I did non-contact surface roughness testing. I want to measure the surface roughness of the worn out specimen surface. I want that I've measured with the non-contact surface roughness tester. Okay, so that is actually we can it possesses a nanotip. If it moves over the surface of the component, the tip may gets damaged. So for avoiding, we can do the finite element simulation of it. That is what the finite element simulation and analytical analysis of nano field emission sources that terminate with a single atom. This is a new perspective on nanotips. So these researchers, this researcher have done this work. That is the tips, nanotips usually characterized in the field ion microscope FIM and field emission microscope FEM. So with which they have used it, and these are actually the highlights. They have modeled it and simulated it with the help of analysis software. That is actually the highlight of this work is actually analytical numerical analysis to a single atom tip FIM and FEM. That is as specified here, like field ion microscope and field emission microscopes. So those tips they have simulated. The analysis exhibit the significant effect of the tip based on the electric field on nanotip apex, and the analysis helps to estimate the tip shape at a mesoscopic scale. And we all know about it. Mesoscopic scale, length of scale, is actually refers to intermediate between long and short, which applies to microstructures to be seen in between the atomic and the macroscopic length of scales. How to study it? That is what this is the tip, and they have modeled it in this way. Again, here the axisymmetric modeling is involved. So they have not modeled the whole tip. So one half of the tip they have modeled, and they have studied about it. And also 1 minute. Yeah. So there is another work where FEA had been accepted for simulations in biomechanics for analyzing stresses and strains in dental implants. And the dentists they use, no, so in those dental implants and the surrounding bone structures. So FEA can be applied in biomechanics also for analyzing the stresses and strains in dental implants. Also, the nanotechnology had revolutionized nano biomaterials, tissue engineering, nano scaffolding. They have nano drug delivery and dental nano composites they have. So in all the fields, we can simulate and we can analyze about stresses and strains, how much it affects the bones surrounding bone structures over the teeth. So all those things can be in the medical field also. FEA is placing a major role. That is what I wanted to insist. And yeah, this is again elastic plastic analysis of ultra fine grind Si2N2O Si3N3 composite. So in which also the development of micro nanotechnology led to the characterization of the mechanical properties at micro nanoscales. Here also the nano indentation concept, the nano indentation test has a diamond indenter to produce indentation load and the penetration depth, which they can measure from the load penetration curve, pH curve, loading and unloading curve. Okay, with which how much load on how much depth has been there on the component. So the pH curve can be used to measure the mechanical properties, as we have seen in the previous cases, to measure the hardness, elastic modulus, toughness, all those things. So there are two methods to derive the material properties from loading and unloading indentation. So experimentally they did it, and also they have simulated it with the help of FEA, and they have compared the results and they have got it. And another researcher, these researchers, they have actually did finite element analysis of sliding wear behavior of copper graphite composite.